So, good morning everybody and welcome. Today we are going to talk about degrees of freedom. It is one of the most fundamental concepts in any subject actually, degrees of freedom. What do we mean by degrees of freedom? As the word suggests, what are you free to change, what are you free to set, okay. So, in a process you would be used to for example counting the number of equations or number of variables and subtracting the number of equations, what is left, that is what you understand by degrees of freedom. When you want to control a process and let us say you are not that mathematically inclined or you are not an expert at modeling, you still need to know what the degrees of freedom of the process is. For example, an operator of a process must know what is he free to adjust. So, he has an understanding of what degrees of freedom are, even though he does not know the exact model for a distillation column or a CSTR or a plug flow reactor or whatever else, okay. So, what we are going to try here is come up with a very simple way of figuring out what the degrees of freedom for a chemical process is, okay. And let us just start with, for example, a simple tank. It is a surge tank, you have got a feed coming in, you have got a feed, you got an outlet stream, an inlet stream and an outlet stream, okay. How many independent valves can you put in? 1, 2, 3, 4, how many independent valves can you put in? No, I am not talking degrees of freedom, we will come to degrees of freedom later. How many independent valves are there for this simple process? One feed in, one feed out. How many valves will be there? Two valves, one at the inlet, one at the outlet, right, okay. Let us say I have got a T junction, okay. Let us say I have got a simple pipe, okay. How many valves can I put on this pipe? How many of them are independent? There is only one independent valve. Is that clear to you? You can put as many valves as you want, but you see you can only set one flow, you are only adjusting one flow, okay. Okay, now let us say I have got a T junction. How many independent valves can we put on this? Let me put it differently. Let's say I have got a tank. Yeah, 2 is correct. There are inlet streams. We are not worried about inlet streams. Let's say I take an outlet stream and I split it into 2. One is feeding, stream 1 is feeding a process train. Stream 2 is feeding another process train. How many independent valves can I put on the outlet side? Only 2, right, because incompressibility dictates that. For example, let us say I put here, then the flow here, this flow F total must be equal to F1 plus F2, right, that is a requirement of incompressibility, incompressible flow, yes or no, yeah. So, first of all you need to know how to put in independent valves, the idea of how many flows are independent, okay. Once that is clear to you, we can look at degrees of freedom, okay. So, if I take this simple tank process, I have got 2 independent valves, one at the inlet, one at the outlet. That is another way of saying I have got 2 independent flows, the inlet flow and the outlet flow, okay. If I look at the steady state material balance around this tank, okay, I know that flow in must be equal to flow out, yeah. What that means is of these two independent valves, of these two independent flows, there is a, of these two independent valves, only one can be set, only one flow can be set independently. The other flow for steady operation must equal whatever flow you have set. So only one of these flows can be set, the other one must match whatever has been set. Yes or no? Okay. So once that is clear, clearly if I put in a flow controller, maybe I should put in controllers in a different, if I put in a flow controller, and I have two set points, set point for the outflow, set point for the inflow. Okay. So F out set point, F in. If I implement this scheme is guaranteed to fail. Why is it guaranteed to fail? Because even though if you put in these set points to be equal, the sensors are never exact. So the inflow may be 100.1 kilograms per hour and the actual outflow may be 99.9 kilograms per hour, even though the set points for both the, even though both the flow set points are the same. Yeah? Yes or no? Okay. आगे आ जाओ, come here. Okay. So this is guaranteed to fail in the sense that either inflow is more than outflow no matter how small the difference, or outflow is more than inflow no matter how small the difference. Yeah. So what that means is the tank level, which is the inventory of the liquid contained in the tank, is either going up or going down depending on the mismatch. Okay. So this is not acceptable, this is not acceptable. Yeah. And this also brings the concept of non-self regulatory inventory. Inventory means here we are talking about liquid inventory. Okay. So the level in a tank is an indication of the liquid inventory inside that tank. Okay. So inventories by their very nature, unless they are matched, either things are building up or depleting. Inventories are either building up or depleting unless it is ensured that in and outflows are matched. Is that clear? So what that essentially means is that we will have to have a level controller, and that level controller may be this way and it sets this set point. Alternatively, and then what we have is the flow in set point sets the flow through the process, flow through the tank. Okay. So F in is the throughput, it's called the throughput, what is flowing through the unit. Okay, that is the throughput through the unit, and then you have got a level controller. Now for a given throughput, is the operator free to adjust anything? Let me rephrase the question. If this is given to you, okay, for example your manager asks you, you have to process so much of feed through this tank. The manager has told you this is what it is, so it is given to you. To run this tank, does the operator have anything that he can adjust? What can he adjust? The most he can do is he can adjust the set point of the level controller. Does that have any influence on the steady state flows? Right. So really speaking, operator has for a given throughput no degree of freedom. Okay. So what have we for this very simple example, what have we learnt? What we have learnt is, well, liquid inventories are non-self regulatory, therefore they must be controlled, because if you do not control it, it is either building up, levels are either building up or depleting. Yeah, that is point number 1. Once you have put in that level controller, okay, for a given throughput, whatever okay, so there's two independent valves. If one of the flows is given, one valve is left, but that is under level control or inventory control. Now the operator has got nothing left to adjust. So what is the degree of freedom as far as the operator is concerned? Running this process is actually 0. It's a very simple process. So now we come to what's called control degrees of freedom. What is control degrees of freedom? Control degrees of freedom is number of valves, number of independent valves. How many valves are there in the process that can be adjusted? Okay. Then there is, so what is the control degrees of freedom for this process? 2. Okay. For this simple example, it's 2. What is the, what should I call it? Steady state degree of freedom, steady state operating degree of freedom. For this process, there are 2 scenarios. Okay. One scenario I just presented to you. Your boss is telling you have to process so much. Okay. So then the inflow is not in your hands, it's set for you, it is given to you. Okay. For a given throughput, the degrees of freedom of this is 0. If throughput itself is in your hands, yeah, then the operator can adjust the flow in set point, and then the flow through the process is whatever it is, and the operator is free to choose it. Okay. In most situations, the given throughput scenario is what is relevant, because somebody from up there tells you production should be this because our estimate of the market demand is this, therefore the production should be this. Okay. So the production is actually, so the throughput is actually given to you. That's the most common situation. Other times what happens is, for example, this inlet flow controller, this may be its flow may be set by the level controller for an upstream tank. Do you see what I am saying? So some unit upstream is setting this flow. Yes or no? Some unit upstream is setting this flow. Okay. So either your boss is telling what the throughput should be, or some unit upstream is setting the flow. Okay. So most common, throughput is not in your hands. It's either set by an upstream unit, or it's told to you that you are supposed to process so much. Okay. So the most common scenario is given throughput, and if I am not specifically mentioning that throughput is given or not, then assume that throughput is given. By default, throughput is given. Okay. Given throughput. The other is that it is actually a degree of freedom. You are free to choose what the throughput should be. Then it is a degree of freedom. Okay. Does that make sense to you? Yes or no? So for the given throughput scenario, for this simple tank process, the degrees of freedom is what? 0. Throughput is given, outflow must be under level control, that's it, you are done. Yes or no? If it is a degree of freedom, then the operator can set what the throughput is. He has that degree of freedom is 1. Does that make sense? Yes or no? We took a very simple example, no equations, no nothing. Okay. Now we will take this. Okay, what comes out of this is, if I am looking at a given throughput scenario, okay, I take the feed valve out because that is the feed to the unit. I take the feed valve out because that's given, that flow is given to me. I count total number of independent valves, and when I say n valves, this is actually excluding the feed valve. If I am excluding the feed valve, that means the throughput is given to me. Okay, so I calculate n valves minus number of I'll call them inventory controllers, ICs. Level is a sign of, is an indicator of liquid inventory. You could also have component inventories, you could have gas inventories. What is the sign of gas inventory? Pressure. Pressure is increasing, that means the gas held up in the unit is increasing. Yeah. Okay. So there are different kinds of inventories. You know, the inventories, you could have how many cars are there in your storehouse or in your whatever parking lot in a dealership. That is the inventory of cars, right. So, inventory is a general term, okay. It could be liquid, it could be components, it could be gas, it could be number of things in my shelf or in my storehouse or in my shed or whatever. Inventory could be of anything, okay. So, I have number of valves or number of control degrees of freedom minus number of inventory controllers, that gives me my degree of freedom steady state. For steady operation of the process, I put in independent valves excluding the feed, count them. So, n valves excluding the feed is actually 1. How many inventory controllers are there? Minus 1, that gives you what? 0. Yeah. So, degree of freedom of this tank, steady state operating degrees of freedom of this process is what? 0. Yeah. Okay. Now, let us take this approach further. Let us see, we have got, let us say I have got a CSTR, a continuous stirred tank reactor, okay. It is still a tank, but now there is reaction occurring in the tank, okay. Liquid phase reaction, so pressure is, will not involve pressure here, okay. So, there is feed that is coming in, there is a stream that is going out. So, this is a CSTR, it is a CSTR, some reaction is going on inside and you are taking out reaction heat by cooling in the jacket. So, this stream is denoting cooling, okay. The jacket stream, this guy is denoting cooling, okay. How many independent valves? 1, 2, 3, okay. DOF steady state, how many do I have to put in a level controller? Do I have to put in a level controller? Yes or no? Will the level in the CSTR, liquid level in the CSTR regulate itself? Is it self regulatory? I have to control it, right. If in is not equal to out, kilograms in minus kilograms out is not equal, well either the level is building up or it is depleting. So, I have to put in a level controller. So, let us just say okay. So, number of valves excluding the feed or excluding throughput, okay, is 2. How many level controllers do I need to put? 1. So, let us say I have put in a level controller that is like this, okay. Now, I ask you a question, in the tank if I changed the level set point, did it make a difference to the steady state solution? If I looked at the tank, if I made a change to this level set point, did it make a difference to the steady state solution? Flows, flow in, flow out, yes or no? It did not make a damn difference, right, okay. Here when I make a change in this level set point, does it make a difference to the steady state solution? What happens to the residence time? Let us say you are operating at 50% level versus you are operating at 80% level. Your residence time changes, so conversion changes, so what is going out changes. The steady state is affected by it. Yes or no? Yes or no? So, since the steady state is affected by it, when the operator changes this set point, he is free to change this set point to get something, to change the conversion of the reactor or maybe to improve the selectivity or whatever, okay. This is something that the operator can change, and as he changes the steady state will get affected, yes or no, okay, alright. What would you do with the cooling duty? You will typically put a temperature controller, right. So, given, so throughput is given, so this is given, yeah, this is not in your hands. So, there were 2 valves and the set point or and whatever is the cooling rate and whatever is the level, these 2 set points affect the steady state solution. So, actually the steady state operating degrees of freedom of this CSTR is actually what, 2. Our rule that we took out was actually broken. Why did it get broken? In the previous case, if the inventory was non-reactive, it would not have affected the solution, the steady state solution. So, we had to discount that valve. Here the inventory is reactive. So, we have to count that valve, because how much amount of inventory you have is affecting your steady state, whether you are operating the reactor at 10% level or 90% level is affecting the conversion that you are getting, yes or no. So, we need some sort of a modification to the rule, and the modification to the rule is essentially degree of freedom steady state is equal to number of independent valves excluding the throughput, okay, minus number of non-reactive inventories. Here the inventory is reactive, okay. So, how much you have in there must be counted, okay. So, earlier I had said number of valves minus number of inventories, yeah. Now we are modifying it, number of valves minus number of non-reactive inventories. Does this make sense? Okay, all right. Now let us come to something slightly more interesting. Let us say I take a distillation column, a simple distillation column. So, here is a simple distillation column. I have got a feed, of course it has a valve, however I am not going to count it because this feed is being set by an upstream process, okay, it is not in my hands, okay. Vapor, condenser, reflux drum, reflux, distillate, there is liquid that accumulates at the bottom, okay. I put in some steam, sorry, before I start asking you questions, I want you to know that this is the distillation column, right. Now, how does the reboiler work? Typically it is a thermosiphon reboiler, okay. What is the thermosiphon effect? It is actually reboiler is hot, the bottom sump is slightly colder, and because of whatever convective effects the liquid actually flows like this automatically. So, there is no pump here to make the liquid flow. You see this out, whenever I show a valve, that means there is a pump that is driving the flow, and the valve can be adjusted to get whatever flow you want, yeah. But at the bottom of a distillation column you do not have any pump. What you have is from the bottom sump liquid is flowing out by gravity, part of it goes to the reboiler, and because the reboiler is hot, you know there is a driving force that sucks in liquid, okay. This is called the thermosiphon effect, okay. You know the siphon effect, thermosiphon because temperature gradient is creating the siphon effect, okay, because the reboiler is hotter than the bottom of the column. So, this flow is by gravity, okay. What is coming out here is vapor, okay, all right. Of course, you have got to draw more or less, you have got a pump here and of course a valve here, okay. And of course, you have got a pump here which I am not showing, you have got a valve here and you have got a valve here, okay. You also have in your hands how much steam you are putting into the reboiler, yeah. You also have a, let us say, a cooling water, how much cooling water you are putting into the condenser to condense the vapor that is coming up the top, okay. I am not showing a valve here, or maybe I can show it and then rub it, and I am not showing a valve here. Why? Because it creates unnecessary pressure drop. That is the basic reason. Okay, it creates unnecessary pressure drop. Then the reboiler, you see there is some pressure. A control valve will always have a large pressure drop. Why is that the case? In any line, if you want to control the flow, whatever you are moving, that will have to have a large resistance. It has to be the controlling resistance, right? If it is the controlling resistance, pressure drop across that piece of valve has to be large. Do you see what I am saying? Otherwise you can move the valve, flow will not get affected because it is not the controlling resistance. Does that make sense or no? So you do not put a control valve there. Of course you will have a valve which is fully open or fully, kind of a gate valve or probably a gate valve which is basically fully open or closed. That valve will be there, but it is not a control valve. Do you see what I am saying? Because control valve will create large pressure drop. Large pressure drop means your reboiler is unnecessarily hotter, because at a higher you will have to operate the reboiler at a higher pressure. At a higher pressure, for the same liquid, it will boil at a higher temperature. Water boils at 100 degrees Celsius at 1 atmosphere, but if the pressure is 5 atmospheres, the temperature will be 130, 140 degrees Celsius. Yes or no? So I do not want to unnecessarily jack up the temperature of my reboiler, right? So therefore there is no control valve here. For similar reasons, there is no control valve here too. And in fact you can imagine, you see this is vapor. Vapor lines are what? Vapor is so much less denser than liquid. Try putting a valve on a vapor line. No, it is not a question of condense. The vapor line will be so big because vapor is less dense and therefore it requires a greater area, otherwise the velocity will be too high. Do you see what I am saying? For reasonable pressure drops, your pipe will have to be large dia to accommodate low density vapor. Kilograms per hour may be the same, however it requires a large. Just try putting a valve there and try moving it. The valve will be expensive like hell, it creates unnecessary pressure drop, right, and moving it will take ages. You got a pipe that is this thick and there is a valve on it and then you are trying to move it, just does not make sense. Okay? So there is no valve here. Does that make sense or no? Okay. So now how many, excluding the feed or excluding the throughput, how many valves do we have? N valves, 5. How many levels do I need to control? Is there a pressure that I need to control? I also have vapor inventory. You see I am boiling vapor, so there is vapor that is stuck inside the column. Okay. What if I am boiling more than I am condensing in the condenser? What will happen to the pressure? It will increase, right? So I need to control the pressure also. Yeah. What is the most obvious way of controlling the pressure? I will put a pressure control. If the pressure is increasing, condense more, then the vapor will be killed or vapor will be condensed and the pressure will drop down. Alternatively, the pressure is decreasing, condense less and the pressure will be where it is. Does this make sense or no? So you will have to have a pressure controller. Okay. So two liquid inventory controllers, one gas inventory, vapor inventory controller. Yeah. So how many inventory controllers? PC 1, total 3. Degrees of freedom will be what? Now if you think about it, and you would have done this in your courses, if you are not getting the desired separation, that means let us say the distillate is getting too much of the heavy key up, too much of heavy key impurity in the distillate, or too much of light key impurity in the bottoms, what will the operator do? If there is too much light key that is dropping down the bottoms, he will increase the steam, so that whatever light component was dropping out the bottom, which it should not be, is sent up. Yeah. If there is too much heavy key that is coming out the distillate, what will the operator do? Reflux more. Yeah. So what are the 2 degrees of freedom? Reflux and reboil essentially, and this comes out in your Macchiappe-Thiele analysis, etc., reflux ratio, reboil ratio, etc., you would have seen in, you know. So the 2 things that the operator has in his hands is essentially the reflux and the reboil. Okay. Usually that is the case. In some unusual circumstances, he may adjust the reflux or reboil indirectly by adjusting the distillate rate or the bottoms rate or some such combination. Those combinations are also possible, but basically he has got 2 things in his hands: how much is putting back into the, how much liquid is being put into the column, and how much vapor is being put into the column. That is your 2. By the way, none of the inventories are reactive. Yes or no? None of the inventories are reactive. Therefore, they had to be discounted. Okay. So, I hope this very simple procedure is clear to you. Now, let us take for example, maybe let us take a plug flow reactor. I do not know how to cook it up, and exothermic reaction is going on in there, and there is some mechanism by which you are removing heat. Okay. What is that mechanism? There are n number of mechanisms or m number of designs for different applications, okay, how you remove heat, but the heat is being removed, reaction heat is being removed. It is a cooled exothermic packed bed reactor. Okay. So, maybe it is a packed bed too, so there is some catalyst in there. Okay. The feed is compressed, let us say it is a gas phase reaction. Okay. Sent to the reactor, it is heated, this is a heater that heats the feed to the reaction temperature. There is a cooling, in the reaction heat is removed using the cooler, and what is coming out is actually I do not know, condensed. Yeah, let us say it is condensed. So, this is a cooler that liquefies the vapor. Okay. Let us just say this is the process. Let us not worry about the compressor. So, there is some feed that is coming in, it is heated, reaction heat is removed, and there is a cooler that condenses the hot reaction effluent. Okay. Yeah. Degrees of freedom, independent valves first of all. Can I put a valve here? Yes, no? I will put it, but then it is set by something upstream, or I am told that this is the amount of feed. Okay, so the valve is there, but I do not count it. Fine, fair enough. Okay. Do I need to put a valve here? Cooling, heating duty. Okay. Do I need to put a valve here? Cooling duty in the reactor. Okay. Do I need to put a valve here? Can I put a valve here? Why? Why? What is a plug flow reactor? It's essentially a straight tube. Yeah. So once you have set the flow through that tube at one location, you can't set it at another location. This is essentially a single straight tube. You are putting in heat here, removing heat here, again removing heat here. All that is fine, but there is no hold up. Do you see what I am saying? This is essentially flow through a tube. Heat exchanger is also nothing but a tube. Material is just flowing through the tubes. Heater is also nothing, whether it's a furnace or a, do you see what I am saying? There is no hold up. Okay. What you are having is flow through a straight tube. Therefore, you cannot put a valve here. Once you have put a valve here, you can't put it here. Does that make sense or no? Okay, so this is the reactor, this is the heater, that's the cooler. Okay. So you can set the flow through this train only at one place, because it's essentially a pipe and there are no drums or surge drums or large hold ups anywhere. Okay. This essentially flow through a pipe. So you cannot put a valve here. Similarly, you can't put a valve here either. Okay, etc. etc. So feed valve is discounted because throughput is given. Total number of valves is then 1, 2, 3. Okay. Degrees of freedom, how much, what would be the degrees of freedom? Now you tell me. DOF steady state, it will be actually 3. What are those 3 degrees of freedom? What is the inlet temperature, outlet temperature, or how much heat you are removing? Outlet temperature, or maybe the reactor will have a hot spot temperature. What is that hot spot temperature? Okay, because the hot spot temperature will set the cooling rate required in the heat removal rate inside the reactor. What about this cooler? What will this cooler do? It is condensing. So how will you decide whether I need to condense more or less? What did you do in the distillation column? If the pressure is going up, condense more. If the pressure is going down, condense less. Same thing here. Now pressure controller is an inventory controller. Basically, how much vapor or gas is stuck inside my reactor system, right? If the pressure is increasing, more gas is stuck. If pressure is decreasing, less gas is stuck. Yeah, so it's essentially an indicator of vapor inventory. I am, however, counting it. Why? I am not discounting it, because if the pressure set point is increased, what happens to the reaction rate inside the plug flow reactor? It will increase. Usually it will increase. If I decrease this pressure set point, the reaction rates will go down, because reaction is proportional to partial pressures. Higher the pressure, right? So in that sense, the degree, even though this is an inventory controller, this inventory must be counted because it is a reactive inventory. It is not a non-reactive inventory. Does this make sense or no? Yes. No, but you see, whatever is the pressure here is the pressure in the reactor. Yes or no? If this pressure is increasing, except for the pressure drop across the reactor, this pressure is also increasing, right? So if this pressure set point is 50 bars, for example, and I make it 60 bars, I guarantee you the pressure inside the reactor has also gone up, save for the pressure drop through the reactor. So maybe this was at 51 bar, and then pressure drop across the reactor was 1 bar, but then when I have increased this to 60, this may be, I don't know, maybe 62 bars or 61 bars, something like that. Yeah. So the moment I change this pressure set point, the pressure inside the reactor also changes. Reaction rate changes. What's coming out of the reactor, the steady state changes. So it is a degree of freedom. right? Yes or no? Okay, therefore it has to be counted, or rather not discounted. Okay. Okay. I can complicate it a little bit more, but okay, now let me get to economics. If you are running this reactor, would you like to run it at a low pressure? Why? Low conversion, reaction rates would be smaller. Okay. So, once the reactor is designed and it is designed to operate at a maximum pressure of, I do not know, let us say x bars, you would typically operate at x bars. Do you see what I am saying? Because that is what gives you the maximum conversion. Yes or no? So, I am counting it as a degree of freedom, but in practice the reactor is operated, or gas phase reactors are operated at the highest possible design pressure. Do you see what I am saying? Similarly, if I go back to my CSTR example, in the CSTR we said that the level inside the reactor affects the conversion. Yeah, if I am operating at a low level, conversion will be lower. If I am operating at a higher level, conversion will be higher. Yeah. Similar to the plug flow reactor or the packed bed reactor, gas phase packed bed reactor, I would always operate the CSTR at maximum possible level. Let us say 80%, because beyond 80% alarm goes off and you have to take some safety precautions, etc., etc. Let us say 80%. Okay, I will always operate at 80%. Do you see what I am saying? However, it is important to realize, I am counting it because it is important to realize that changing that affects the steady state solution. In practice, I am always operating at maximum level. I am always operating a gas phase reactor at maximum pressure. However, from a steady state point of view, it is important to realize that the pressure, operating pressure and the operating level of a reactive volume, of a reactive inventory affects the steady state. Therefore, I am counting it. Okay. But when I am running the process, I will always choose the value of this and that to be maximum allowable, because that gives me the maximum conversion. What does that do? It reduces the separation load downstream. There will be lesser unreacted reactants to be recycled, that cost goes down. Okay. So, in practice you will find that there are always very reasonable values for the different degrees of freedom that you have. But first thing you need to realize, how many things am I free to set. Next thing is, what is the best setting. Now what I am telling you is the best setting for the level set point or the pressure set point in a CSTR or the packed bed reactor, gas phase packed bed reactor respectively. You see what I am saying? Okay. So first I know that this is my degrees of freedom, I am free to set this, this and this. The next is, how do I set it? What value should I set it? That is a separate question. But in terms of degrees of freedom in a CSTR is, the way I have drawn it is 2. Degrees of freedom of the packed bed reactor system, the way I drew it was 3. Okay. Alright. Now let us take a process. Let us take a complete process. Okay. And we will probably take the simplest, 3 is also drawn, 4 is also drawn, 5. Okay. Let us take a simple, I do not know, A plus B goes to C type of process. So here is a CSTR. Okay. I do not know, A plus B goes to C. This is the reaction that is occurring inside the CSTR. Okay. You are putting in fresh A, you are also putting in fresh B. So let us say you are putting in fresh A, you are putting in fresh B. Reactor effluent is distilled in a distillation column. simple distillation column. A and B will typically be, obviously because the molecular weight of C is the molecular weight of A plus molecular weight of B, C will be the heavy component, right. So, A and B will go up, C will go down, yes or no. Okay. So, I have got this reflux drum, A and B come up the top, because A and B are precious raw materials, I do not want to dispose them, so I am recycling them, right, and C comes down the bottoms. So, this is nearly pure C product and this is essentially AB recycle. This is my process. Now, first of all, draw me independent valves. Next, tell me the degrees of freedom. Here throughput, let us say, is counted. What is the production rate of C that you want is in your hands. Okay. Tell me the degrees of freedom. First of all, valves. Will there be a valve here? Okay. So, there is a valve here. Will there be a valve here? Okay. Will there be a valve here? Well, distillation column, you all know how it was drawn, so you can just copy paste. Will there be a valve here? No. Will there be a valve here? Exactly, because this flow is set, this flow is set, this flow is set, and this has to be this plus this and this has to be this plus this. Yeah. Alright. So, these are the valves. Okay. How many total valves? 1, 2, just a second. Let us say it is an exothermic reaction and I am removing some heat. Usually reactions are exothermic, some of them are endothermic too. So, how many valves? 1, 2, 3, 4, 4 plus 5, 9. Okay. If I count all 9, that means throughput is a degree of freedom. I am counting throughput as a degree of freedom. Okay. My production rate of C, so many kilomoles per hour or so many kilograms per hour, I am saying that that is also counted. Okay. So, 9 valves. How many non-reactive inventories? Non-reactive inventories. 2 levels, 1 pressure. Okay. Degrees of freedom? 6. What are those 6 degrees of freedom? 2 for the column, reflux reboil, 2 for the temperature and level, okay, and 2 for the 2 fresh feeds. Does that make sense or no?
How did you get 3?
2 levels, distillation column top, distillation column bottom, and pressure of the distillation column, vapor inventory 3. Okay. Total valves were 9, 3 of them are going to get used for inventory control, vapor inventory, liquid inventory. Okay. That leaves me with 6. Yes, of course, non-reactive. Reactive is being counted. Okay. That leaves me with 6. So, degree of freedom of this process is 6. Okay. So, the operator can set 6 things independently to run this process, and in those 6 things the production rate is also one of them. If I exclude the production rate, saying that the production rate is given to me by my boss, then the operator can set only 5 things. Okay. What would those 5 things be? So, let us say flow rate of A is my throughput, that's given, I have to process so much of A. What would those 5 things be? What is the temperature of the reactor? What is the level of the reactor? How much reflux you are putting into the column? How much reboil you are putting into the column? 4. And recycle rate. Recycle rate, or maybe you can call it the total B that is going, either one of the any one of the flows in the recycle loop. Okay. Another simple way of counting degrees of freedom is, well, 2 for the CSTR, which I know, 2 for the column plus as many fresh feeds as there are, so 2. So 2 plus 2 plus 2, 6. That is also another simple way of doing it. Okay. You do not have to count equations, you do not have to count number of independent variables, you just look at the process, put in independent valves, count the valves, discount non-reactive inventories, that is the degrees of freedom of your process. Does that make sense? I think this is a good point to stop today's lecture.